Same thing, right? All right, and then how do I solve that?
All of the T's be TB here and
Yeah. Because we've set it equal to the one that we got from the energy balance. So the only time that those two conversions will be the same is at equilibrium. Right? So this is only true when you're dealing with so no questions here? So how do I solve it?
Algebra.
It might be algebraic, it would be messy.
It'd be really messy.
Yeah.
Solve.
Wolfram alpha?
Huh?
Wolfram alpha?
Sure.
Solve.
Solver, Wolfram Alpha, your calculator. Everybody knows how to solve this. This isn't one I need to pull up Excel to demonstrate. And what you get is the equilibrium temperature is 460. And the equilibrium conversion is 0.4. Okay, we're going to continue the example now with multiple reactors. Yes, I'll erase this. All right, we'll keep these numbers in our head because we're going to use, it's going to be the same system. All right, so we have 3 PFRs now in series, and between each PFR we have a heat exchanger. So to be consistent with what we had earlier in the semester, we're going to call that X1 and that T1, okay? And this one we call TO2, T2, X2, TO3, T3, X3. Yes?
Can we assume that the converter can change in the heat exchanger?
Why would the conversion change in the heat exchanger?
Because as you cool, couldn't you have your product be less stable?
I mean, yeah, you could certainly imagine some situations in which reaction is occurring in the heat exchanger, but assume that this is just a heat exchanger. All right, so again, the same example, so the same heat capacities, the same delta H of reaction. And now we're going to say that in each reactor, it's large enough to give us 95% of the equilibrium conversion. Same feed temperature to the overall unit. Okay, so on reactor 1, what's the outlet conversion?
0.95 times 0.4.
0.95 times 0.4. Right. So we've already solved it. the outlet conversion is 0.95 times 0.4, which I think is 0.38. And so the outlet temperature is 0.95 times 460, right?
No.
No,
No.
no.
You have to go back.
Imagine if it was 0% conversion, right? Then the outlet temperature is going to be 300, not 0. So how do we get the outlet temperature?
Go back and plug it in.
Go back and plug it into what? Which equation?
Energy balance equation?
The energy balance equation. Which one do I use for convenience?
Temperature?
Of course, temperature as a function of conversion. So let's do that. We had the delta H is negative, what was it, 20,000? Correct? Times the conversion now, x1, not the equilibrium conversion, but x1, which is 0.38.
Is this T1 or T2? This is T1.
Sorry. Yeah, T1. And then the heat capacity terms, 50. And we only have it for A. So it's 50 times the initial temperature, 300. And then delta CP was 0, so the third term, if you're looking at your notes, goes away. So that's conversion times delta CP. And then this whole thing is divided by, again, 50 plus, again, conversion times delta CP. If you do the math and you substitute in that's equal to 0.38, you get 452 Kelvin. So one thing I'll put on the board, because I do think it's a useful simplification to have in your notes. This will now be the third time that I've written this out today. Oh well. So this is the form that you were given, and this is the form that you should have in your notes or on your cheat sheet. But there's one simplification of this that's going to happen enough that it's worth writing it out. Okay, everybody's familiar with that one. Like I said, I put it up 3 times. Delta CP is either via simplicity or because they've rigged the problem to do this, often going to be 0. In those cases, what does this simplify to?
Delta H reaction TRX over the sum.
T naught, because this cancels out, but only from that term, plus negative delta H reaction divided by the sum of the heat of the big thetas times the heat capacity. Times conversion. So that's a form that you're going to use enough that it's worth having in your notes. Just make sure next to it that you make it clear that that's only valid when what?
Delta CP is 0.
Delta CP is equal to 0. Right. Okay, anyways, 452 Kelvin. Now things get a little bit more interesting. Has everybody got this? Because I'm going to erase it all. Okay, so this is 452 Kelvin, right? And this is 0.38. And I think I forgot to put something up on the problem screen. that's weird. I don't see where it says how much the heat exchangers are actually doing. It's not a problem though. I mean, we can start the problem anyways. Okay, so what equation do we use for reactor 2?
Do we assume it was about down to 3 Kelvin?
No. Don't worry about the temperature drop. The temperature, it could. I just say let's not do that because he actually puts numbers in here later, and I don't think that's what it does. It might, but his problem statement doesn't actually say it.
Well, we know the CP is 50, right, so can we just factor it in? But you have like.
We don't know the heat. We don't know the heat load on the I mean, obviously something has to be given. I just didn't see it. It's not a big deal though. Again, let's not worry about that. How do I just solve? How do I set it up mathematically?
So
Do the same thing, find the intersection of the equilibrium of the energy balance in terms of temperature and in terms of.
Okay, so let's write out the equation for the energy balance. Wait, this isn't the long we used. So what is this